Okay, so if you're interested in the bonus top problems for what day would that be? Monday. Here's the two things: reflections in the y-axis and horizontal shrinks and stretches. Okay, so let's start with the easier of the two, the reflections in the y-axis. And it's really not bad at all. If you're just trying to figure out, well, I guess what's the way we should think about it? Here, let's just do one over here to the side. Let's do a good one. Let's do a graph you haven't seen before. Let's do y equals x cubed. Okay. So if I start plugging in numbers, if I plug in 0, 0 cubed, 1 cubed, 2 cubed, negative 1 cubed, negative 2 cubed. Okay, so this will get me an idea. And I'll just think about, oh, does that hold up? Here's what I mean by that. Oh, negative 8. So if I kept going to the right, 3 cubed 27, 4 cubed 64, yeah, that thing is skyrocketing over this way. Okay, so there's an x cubed graph. A lot of people call it an S-curve based on how it looks. All right, now what you do know how to do already, here I'll do it in different colors so you can tell the difference. We know what happens when we just stick a negative out in front of the function, because it just takes the exact same x's and gets out the opposite answer. Like, we're still going to take your x and cube it. We're just doing the opposite of what we got before. Remember, that's a reflection about the x-axis. So that would look like this. Okay, I just took and I flipped it over the x-axis. Okay, now here's the thing about this. Sometimes it looks the same no matter which way you reflect it. So just think about how it all came about. I took those x's, a 0, I cubed them, and then got the opposite. 0 cubed 0, the opposite is still 0. I plugged in the 1, cubed it, got a 1, and then got the opposite of that. So we had 1, negative 1 on it. Okay, so reflected about the x-axis. Okay. This one is going to be reflected about the y-axis, the thing we learned here. Let's do a red one. So I want to flip it this way. So basically what I want to do is take this point that sits right here and reflect it to there. Like, I can tell just by what it would look like. I was like, oh, I'm going to spin this around here. I know there's going to be a point at negative 1, 1, because that's where that point would land. Okay. Oh, gosh. Yeah. Undo. Come back. Okay. That 0.28, if I reflect it over the y-axis, it's going to sit here at negative 28, right? If I reflect over the y-axis, this 1, negative 1 is going to flip to, I said negative 1, negative 1 is going to flip to 1, negative 1. Like, it's going to be the same shape. Oh, gosh, that's really gross looking. As what it was when we reflected around the x, because when we reflected around the x, like this 0.28 came down here to 2, negative 8. It's just the fact that we're folding it a different way still ends up looking the same. But the way you make that happen is, okay, I'm going to take whatever this x value was, 1, but I want to see what happens when I flip it over here to negative 1. I want to take this x value 2. What happens when I flip it over the y and flip it to negative 2? So I don't want to plug in the same x as I was plugging in before. I want to plug in the opposite x's. So to reflect about the y-axis, we plug in the opposite x. So we're going to take that original function, the parent function, and go, okay, well, what would happen if I plugged in the opposite x before I cubed it? Because that's what I did. The opposite of 2 is -2. What happens if I plug that in instead? Well, on this one, it just so happens to give you the same thing, because x cubed is still x cubed. The opposite, a negative cubed, is still a negative. So it's still the same shape as this, but you're thinking about it in a different way. Does that make sense? Okay. So if you ever want to know what's going to happen if we reflect it over the y-axis, or what the equation is going to look like, let's see, what do we do right here? We did that. Write a function h whose graph is a reflection in the y-axis of the graph of f. So we're going to say, all right, then h of x, I want to take the regular old function and see what happens when I plug in the opposite x. Okay, so I'm going to come back up here. And where that input is, I'm going to put the opposite of x. Now, what I would do when I was writing that is I would take in here, factor that negative out, because that lets me compare it back to the original parent function. So if I were to compare this to the parent function, it's going to go 3 places to the right, up 1, and it'll flip it over the y-axis. Okay, so just think about absolute value, flip it over the y-axis. So now here's the thing. An absolute value, when you flip it over the y-axis, looks exactly the same. So it's kind of confusing about what's going to happen right there. So really don't lose just a whole bunch of sleep. But as far as what our graph would look like, again, comparing it to the parent function, which is what can happen if I factor that negative out right there. If I go 3 to the, original function, flip it over the y, it looks exactly like it looks now. I go 3 to the right and up 1. And there's this function. Okay, let's see if we're right. Mine looks like it's going through 1, 2, 3, 4. Looks like it's going through 0, 4. So if I come right here, and it doesn't matter which of the two you plug it into, you can plug it in here or here. If I plug a 0 in, yep, I get a 4. So I feel real good about that graph. Okay. If I want to compare it to this one, which is what the problem was, like I got it back to where I could compare it to the parent. Let's compare it here. This sends it 3 to the left and up 1. So this is the blue one. And notice how if I folded that graph over the y-axis, see how they would lie on top of each other? So we did our job. Okay. All right. The other one, horizontal, shrinks and stretches. So let's just compare one. What will be a good one to use? Let's do one you've never seen before. Let's do x squared. Okay, so if I graph y equals x squared. Oops, come on, right. Zero squared 0, 1 squared is 1, 2 squared is 4, -1 squared is 1, -2 squared is 4. There's my parabola. I don't know if y'all know that word yet, but that's what we call that shape, a parabola. It's a quadratic function. It looks like that. That's the parent shape, or the parent function when we get to quadratics. We know that if we just multiply that function times 5, that's going to stretch it vertically. If We multiplied that function times a fifth. That would compress it vertically because it would be a fifth as high because you're just affecting the y values. Now it gets a little dicey when you change what's happening to the x. So like say we put a 3 right there in for the input before we ever square it. Okay, when you put a number in with the input value, it basically does what you don't think it will. Like most time you think, oh, times 3, that's going to make it grow. But if you put it in with the x is run side to side. That's horizontal. Okay, so putting a 3 in here, well, think about this. If I did actually multiply that out, it's 9x squared. Like vertically speaking, it definitely is going to stretch it because it's going to be a whole lot. I guess the y's are going to be 9 times as high as they were before. But when you vertically stretch one, horizontally, you're compressing. Okay? Like, I don't know. Maybe let's just use this graph right here. And I probably put that piece of graph paper on here for example A. But let's just use it for what I'm talking about because it's easier to see it if you actually put points on the graph. So 3 squared is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So I've got 1, 1, 2, 4, 3, 9, negative 3, 9. Remember, this is just y equals x squared. Negative 2, 4, negative 1, 1. Okay. So what I'm wanting to do, like we said, I'm going to triple the x before I square it. Okay, which, yeah, turns into a 9x squared. So think about this. If you were to plug into that, it doesn't affect this point right here. 0, 0 is going to stay put. If you plug in a 1, though, we're going to get a 9 out. So over 1, up 9, which negative 1 would give you a positive 9 as well. Okay, see, definitely we've got ourselves a vertical stretch because see this point right here? It was 9 times higher in that green one than it is that blue one. Okay, but when you're thinking of it horizontally, you compare. It's kind of one of those things. It's like, okay, how do I get out the same answer though? So like if I wanted a 9x squared, that's what I'm working, and I want to get an answer of 1. That means x squared would have to be a 9th. X would either be plus or minus a third. So if I go to a third, right there, I'm up 1. If I go to a negative third, I'm up 1. So to be at the same y value as I was before, it's like when we stretch it vertically and compress it vertically or shrink it vertically, we're looking at the exact same x and what happened with the y's. When you're talking about a horizontal stretch or shrink, you're thinking about the x values. So like what x values gave me the same y's? It's like, how do I get that 1 out? Okay. So see, notice how by putting a 3 in before you put the x to get the same answer out as before, compare it. Here's 1, here's a third. It was a third of the distance horizontally to get that same y value. So that's a horizontal shrink. Okay, like this right here would be considered a horizontal shrink by a factor of a third. Because your distance you go horizontally is only a third of what it has to be normally to get to the same height. Okay. So on something like this one, it says, here's our original function. Write a function g whose graph is a horizontal shrink. Okay, so we're shrinking it, which means the number you're going to multiply the x by is going to be bigger by a factor of a third. I just did the same one. So we want to take and plug 3x into that function. And you can write it like that. That's fine. Most of the time, folks will, I shouldn't say most of the time. Personally, I usually turn it back into that because then I'm comparing it back to the parent function. Because compared to the parent function, it's still going to be a horizontal shrink because I put the 3 in there where the x is. I'm going to move the parent function 1 to the right and down 5. Now, up here, they were comparing these. Like, take that graph and horizontally shrink it, compress it. So it's like this time we're compressing the the values of the points. So we're shoving those sideways. When you do vertical shrinks and stretches, you're stretching them up and down. And it's one of those things, like the first time you ever hear this one, it makes no sense at all. You're like, oh my gosh, what are you doing? And after about a week, eventually it makes sense. Well, a lot of people just memorize it. But it's kind of one of those things where, like, what would be a good example? I don't know. Let's put this in there. But compared to the parent function, this is a horizontal stretch because that 1/5 is in with multiplied by the argument with shifted 2 to the left and down 9. Because it's kind of one of those where if you're trying to get out, actually, let's not even make it do all that. Let's just make it do a 5th x because otherwise we've got too much going on. You're sort of thinking this way. I've got x's, but the part before I do the absolute value is a 5th x. And then I'm going to get out a y. When on the original parent function, you just plug in whatever x is and you get out y. So absolute value 0, 0, 1, 1, 2, 2, 3, 3, etc. Okay, so you got to think about, well, what, like I would need this part right here, the 1/5 x. If I want to get out a 0, I need that to be a 0. What did x have to be? 0. Okay, so if I want to get out a 1, that means the 1/5 x is what I'm going to take the absolute value of to get out the 1. Well, x would have to be, I want that to be the 1. That means the x has to be a 5 because a 5th of 5 is 1, and then it's true. So this is what you're hoping happens when you actually do the arithmetic, but where the point was 1, 1 before, now it's 5, 1. Because you stretched that x value out to 5 where it would have been at 1. Yeah. Okay. Like I said, this is why y'all wait till pre-cal to do these. They're not easy. They're kind of counterintuitive a little bit unless you just really tear it apart. So if you spent the last however many minutes listening to this, thank you. But and try the bonus, see what you think, but do not stress out over it. Okay, you're going to be fine.